Okay, let's get started. So I hope you had all gone to the guest lecture and it was interesting. We will continue from where we left off 2 classes ago when we were talking about remote procedure calls. Okay, so today we are going to talk about remote method invocations, but also talk a little bit about other types of specialized types of RPC call. Okay, and then we'll talk about RMIs, which are essentially RPCs in the Java world. See some differences between RPCs that we studied last time and RMIs. But let's first talk about other types of RPCs, starting with lightweight RPCs. Okay, so the implicit assumption when we have been talking about RPCs has been that the calling process and the called process, the client and the server, reside on different machines. Okay, we talked about how the machine set up a TCP connection and how to find the server and all of these details. Okay. Now it is often the case that the two processes, the client and the server, are just distinct processes on the same machine. Okay. You can have a distributed application where components of that application might run on the same machine, other components might run on other machines. Okay. You might have more than 2 components. So what happens if you make an RPC call from between 2 components that reside on the same machine? Okay. You could use the traditional RPCs, that will work just fine because it makes no assumption about where the callee and the caller are. They could very well reside on the same machine, everything will work just fine. Okay. But then the question is, can we make it more efficient than standard RPCs? Okay. That brings us to this notion of lightweight RPCs, which is a special case of standard RPCs where the caller and the callee reside on the same machine. And then we'll see how you can use this extra information to optimize the processing of the RPC. Okay. Now, as you realize, when you have standard RPCs, you have to actually send a message from the caller process to the called process. Okay. It's a TCP message, or it's a message that uses TCP. Okay. Now you should ask, what could we actually make more efficient in this process if I told you both of those processes are on the same machine? They still have to communicate. Right? You have to make the call. The call has to still be a remote call, except that the 2 processes are actually on the same machine. Is there something we can do to optimize this communication overhead? Yes. Yes, good one, good point. So what would you do? So the point being made is, if the 2 processes are on the same machine, why do we need to use the network stack? Because you are not communicating over a network. Okay, or if you actually use standard RPCs, your packet will go down to the OS, then the IP layer will realize it's actually meant for a process on the same machine. It will come back up and be delivered to another process. Okay, so you paid all that protocol processing cost, but you could avoid that. What would you do? How else could 2 processes on the same machine communicate? Yes. Okay, shared memory. So if you remember, when we started with distributed communication, I said there are 2 forms of communication, explicit and implicit. Explicit involves message passing, and implicit involves sending data between processes using a shared memory region. Okay. So you could now think of constructing an RPC system for this special case where both processes reside on the same machine, but they have a shared piece of memory. They can read or write to that memory region. So rather than sending explicit message, why not construct the message as a buffer and simply write it to that shared memory region? The other process comes and picks it up from there and processes it and sends back results. Okay. That's the optimization. That's the only thing you really need to know for lightweight RPCs is they are going to use shared memory to communicate instead of actually using explicit messages. And you will see that there is actually some additional details of how you make that. You could have actually declared a shared memory region, which is an OS level construct that allows you to share memory, but there are some other ways to do it, which involves using specialized system calls. So what you will do is use a special call called memory mapping, which will allow you to take a memory region from one process and share it with another process, as opposed to a shared memory region, which is an independent piece of memory accessible to two processes. Okay? It doesn't matter, it's the same concept. So what you will do is when the RPC call executes, it will come to the stub. The stub will realize that this is actually a call to the same process. So rather than making a TCP connection, it will actually use what is called a memory mapping system call that will allow it to take a memory region, which is essentially the stack for the process, for the function that's being called, and share it with the other process. And the other process can take the arguments from the stack, execute the call, put the return value, and then you come back to this process, you have just executed that call. Okay? So you are using some memory management techniques in order for processes to send information back and forth rather than use it explicit messages. Okay? Now this concept of lightweight RPCs was actually first arose in the Solaris OS, which was also the OS where the first commercial RPC system was implemented. Okay, so this was a specialized RPC system, and here's a picture that essentially shows you what is going on. It doesn't actually show the memory region that is shared, but that's explicitly what's happening. So you have something called a door call, which is essentially a lightweight RPC call that is calling a certain function. And then what will happen is there would be a stack in this process. That stack will actually get shared with this other process. So you can push your arguments on that stack, share it. This process can pick those arguments from the stack, execute the call, which is that call up there, and then send the return values by putting it back on the stack. Okay? So you have avoided network processing overhead. You're simply using memory to pass data back and forth or invoke a call back and forth. Okay? So that's the concept of lightweight RPCs. Now, in some systems, you don't have to decide a priori which of the two types of RPC calls to use. Okay? You can actually use a runtime bit to optimize, saying in this case, because you can write the code in one way and say either the processes are running on different machines, use standard RPCs, or the processes are running on the same machine, use lightweight RPCs, and the runtime system will choose the right way to invoke the RPC call. Okay. In other systems, you have to decide a priori whether you have to use standard RPCs or lightweight RPCs. If you use lightweight RPCs to write your code, that code will not run across multiple machines because it's implicitly assumed that it's written for execution on the same machine. Okay. So you have different runtime systems that allow you to do different things. The one in Solaris allows you to use a runtime bit to choose between lightweight RPCs or standard RPCs. Okay. Now that was lightweight RPCs, but there are many other RPC systems that give you different kinds of semantics. Okay, we'll talk about three specific ones here: asynchronous RPCs, deferred synchronous, and one-way RPCs. Let me see if I have a picture here. Maybe the picture. Yes. Okay, so that's best explained with a picture. So this is the timeline for you making synchronous RPC call. Standard RPC call are synchronous, which is when you make an RPC call, that function is going to block. It's going to wait for the reply to come over the network before it comes back with the return value. Okay? So that is best shown using this timeline. So the top is the client, the bottom is the server, x-axis is time, dotted line means that that process is blocked, the thick line means the process is executing. Okay? So initially the client is executing some code, it makes an RPC request that triggers a request to the server. Server executes the RPC request, sends a reply. The client is blocked, which means it's synchronous. Synchronous is same as blocking. And then the client takes the return value, continues execution. That's standard RPCs. Okay? Synchronous RPCs. This is asynchronous RPC, okay? Non-blocking. Asynchronous always means non-blocking. Okay? So what does non-blocking means? Essentially, you're not going to wait for the RPC call to execute. Okay, you are simply going to make the call and continue execution. Okay? In this case, the client is executing, it makes the call, but it waits for the call to be acknowledged. It's not waiting for the call to be executed. It waits for the call to be acknowledged, saying the server received the call. Okay? And then you will see that it continues execution, and the server is asynchronously executing that RPC call while the client is executing. And the return value comes back at a later time. Okay, just non-blocking. And we'll see there are other variants of non-blocking as well, where you may not even wait for an acknowledgement. You just simply make the call and continue. You let the OS deal with actually sending the request at all. But this is the simplest version where you at least wait for the server to have received your request, but not necessarily executed the call. Okay. This is deferred synchronous RPC, which is essentially two asynchronous RPCs in reverse. Okay. The first RPC call is to actually make the request to the server. The next RPC call comes back from the server to the client to return the result of the RPC call. Okay. So here you have again same x-axis is time, top is client. So client executes, makes the RPC request. You get an acknowledgement from the server saying RPC request has been received. Client continues execution. The server has asynchronously executed now the call, but it has produced a return value, okay, which has to be sent back to the client. Okay, and that return value is actually sent as a asynchronous call in the other direction. Okay, so you basically return the value as a RPC call, and then asynchronous RPC call. You get an acknowledgement saying the client received it, server continues to do something else, and the client can then get the return value and do something with it. Okay. So it's basically pair of RPC requests, one in each direction. Okay, both asynchronous. Okay, and then there is of course one-way RPC, which is essentially asynchronous RPC, where the client is not even going to wait for an acknowledgement from the server, meaning that you just make a request and then you just continue execution. So in this case, if I don't have a picture for it, but you can imagine the asynchronous RPC picture where the client just continues execution after making the request. There is no acknowledgement. Okay, that's why it's called one way. You send a request and you just continue execution. Okay. So different semantics from your RPC runtime that give you somewhat different behaviors. Okay. By default, what you have in RPCs will be synchronous, but there are all these other modes that you might have in your runtime. Okay. Question in the back. Okay. Question is, in asynchronous RPC, how does the server return the out? So if you actually need the results to be returned, you're better off using deferred synchronous. But there are many RPC requests that might just change the state on the server. In that case, you don't really need a return. It may be a void a function call where there's no return value. In that case, you would use this. If you actually have a return value, you would have to do something like this. Okay. Any other questions here? Okay, so that's deferred synchronous. We did one-way RPCs. So with that, we are going to change gears, move on to the next module, which is remote method invocations, or RMIs. Okay. So these are essentially RPCs in the object-oriented world. Specifically, we are going to look at this in the context of Java, okay, which is essentially all classes and objects. That's how you are going to write code. And the question is, how are you going to use RPCs or notions of RPCs in this scenario? Okay. So whereas RPCs essentially apply to objects, in the way we are going to extend this notion of objects having methods on them to include RPCs is to have some methods do invoke remote methods. Okay. So think of a class that you write, okay, in Java. Okay. Typically, the class is going to have some state or some variables, and then it's going to have a set of methods. Okay. Typically, the methods are called by other objects, and they make some changes to the state of the object. Okay. Now imagine that some of these methods are being invoked by other processes, other objects residing in other processes, rather than objects within the same process. And now you got RPCs essentially in the object-oriented world. Okay. So rather than just having arbitrary functions, the remote procedures you are going to call in this object-oriented world are essentially methods that belong to some object or the other. Okay. So when you write your objects, you have to decide which are local procedures or local methods, which are remote methods. Remote methods are the methods that this object is exposing to other processes. Local methods are the ones that's exposing to other objects within that process. And private methods are the one it exposes to no object at all. They're local to that object or class. Okay. So if you've done any Java programming, you'll see that this is a nice generalization of taking a local method and now allowing remote invocation of that method, and hence it becomes a remote method. Okay. Beyond that, everything else we learned in RPCs is more or less the same. You are going to essentially not have to deal with low-level issues of where does the object reside, what machine, what is the IP address. All of that is dealt with for you by the runtime system or the stub code. Okay? Those concepts are still the same. You are just going to call object1.foo and pass some arguments. It doesn't matter to you whether that foo is actually a local method invocation or a remote method invocation. In this case, the JVM runtime will decide what it is and do the right thing for you. Okay? Very similar concept as RPCs, where the networking details are not actually dealt with by the programmer, they're dealt with by the stub code. Okay? Same is going to be true here, and there's a picture that you can see, which is very similar to the RPC picture. Okay? In the case of Java, the stub code are called proxies and skeleton. Okay, essentially, it's the client stub and the server stub. They have specific names. It's different terminology, but it does exactly the same thing. Okay, the client stub is called a proxy. The server stub is called a skeleton. Okay, you will see on the server that box there is essentially an object. It has a state on the object, and it has an interface. It's exposed to the outside world, which is a set of remote methods. Okay? And in this case, the client is going to call a method on that object. Okay? But you will just write code as if it was a local object. Okay? And then it will come to the runtime system, or rather the stub code, not the runtime system. The stub code will realize that it's a remote object. It will essentially marshal the argument, construct a network packet, set up a TCP connection, send a request over. Okay? And then that request will come to the server stub. The server stub will look at the message and say it's called a method on that object. It will actually invoke that method, execute it, get the results, send back a reply as another network message. Okay? Exactly what happened in the RPC case is going to happen here. Okay? The terminology is a little different. Marshalling and demarshalling of arguments is going to be called serialization and deserialization. That's the standard term in Java that allows you to actually do the equivalent of marshalling. You can use that for other things as well if you use Java serialize, deserialize. Okay? The stub codes are called proxies and skeleton, but beyond that, it's all the same stuff. Okay? So here you write your code in an object-oriented fashion. You will have classes, you will have objects, but not all objects will be in the same process. They will be distributed across multiple processes. The processes may reside on multiple machines. You just call methods on objects. Okay? Just as you call methods on objects within a process, some of these methods are going to invoke remote methods, okay, on remote objects. Yes, question.
Did you have like a copy of the methods in your local machine so that if there's a network failure, there's a recipe for that?
Okay, so you asked two questions. I thought you were asking the first question, but then you asked the second. So the question is, should you have a copy of the methods on the local machine? Okay, and what happens if there's network fails? Should there be a fallback plan? There are actually two different questions. When you essentially call a method on a remote object, you have to actually have imported the interface of that object. So you need to know what the object is, what kind of arguments to provide, and so on. In the same way, the server machine should have published its interface so that other clients can import it. Okay? So you do need to have a copy of the methods on the local machine so you know what the methods are, what the arguments are, and so on. Okay? That's binding. The second question is, what happens if there are failures? Okay? If there are failures, you are not going to actually have a copy of that object here and start executing it locally. You have to have some other ways to handle faults. And we talked briefly about failure handling of RPCs, which might involve everything from returning an error to retrying and other things. Okay? There's no replication here yet. Okay, yes, question.
So as a programmer, when I refer to a particular object, I would use the variable name. Is that the same thing that's used on the client side to identify an object on the server side?
Yes, so you will just have object foo. Right? You will say foo dot method 1 and then pass some arguments. You will do the same thing. It just happens that the object is remote, and hence methods invoked on it are also remote. Okay, so you'll have essentially you will have local objects and remote objects. When you call methods on remote objects, you are calling remote methods.
Right. So in the first case in RPCs, you said that the server would publish whatever it's being able to serve. So does that mean that every object is also publishing, saying that this object with the name foo or car?
Right. So the question is, in RPCs, the server had to publish its remote methods, okay, and also register itself in the naming service. And the question is, does every object actually have to publish its interface. The short answer is the server process will register itself and expose all the remote methods that it's exposing to the outside world with the naming service. So if there are 3 objects in there, each object is, not every object has to expose itself, but any object that is exposing remote methods has to be registered and the client has to be able to report it. That is indeed correct. Okay. Any other questions? Yes.
You have a method that changes an attribute of a class, and then you have that as a remote method. Will that only change the attribute in the remote process, and then your original process won't actually have that change?
Okay. Question is, if there's an object, let me state the question, see if you're asking what I think you're asking. If there is a remote method, a remote object that has some local state, some variable, you make a method call that changes that variable, right? You are asking, will the local machine actually see the change? Is that what you're asking? Okay. So as you will see here, this is the object. Okay, there's only one copy of it, which is on the server. There's no copy of it on the client at all. Okay, it's not like there is a there could be other objects here. They are distinct objects altogether. Okay, so you can make a call saying add 1 to this variable, and then you may add 1 to a local variable that has changed the state of that object. Okay, that change will be visible to subsequent methods that are invoked on that object. Doesn't mean that there's a copy of the object here, but that if you make another call saying what is the value of that variable, you will get the new value. Okay, so in that sense it's visible, but you are not replicating the state or the object itself. Other questions? Okay, so now what this has actually done is allows us to distribute our objects across multiple processes. Okay, so now you are writing a distributed application by deciding what objects reside in your application, which ones reside on the client, which one resides on the server, or if there are n processes, which one reside in what process and how they are distributed. Okay, so we basically written a distributed application using Java concepts, and now all of this is just more details. I said proxy is the client stub, the skeleton is the server stub, everything else is the same as in the RPC world. The client has to figure out where is the server running, what is the endpoint, which is what's the IP address, what port number to contact it on. It has to do marshalling and demarshalling, which in the Java world is called serialization. Serialization takes any arbitrary data structure and converts it into a byte stream. Okay? You can write that to a disk if you want, not that you will do it here, but Java serialize, you typically serialize an object, write it to disk. If you deserialize it, it reappears as you wrote it. Okay, you are going to use that same concept, but to marshal arguments and send it over a network. Okay, so this is basically how Java would do it. And on the server side, you have to do deserialization to reconstruct the parameter and the call that was made, and then take the parameters and send it off to your the server. Now note that unlike in the RPC world, even in the Java world, you are going to be able to run on heterogeneous machines. Okay? But you don't have to deal with the external data representation and things of that sort in this case. Okay? The reason is all Java code runs on the JVM, which is an abstract representation of a machine. So the architecture, quote unquote, architecture of this JVM, which is abstract machine, is the same across all platforms. It doesn't matter what the underlying hardware is. So basically your messages should work as is, because the object representations are similar despite differences at the hardware level. Okay? Because the serialize, deserialize will take care of that for you automatically. Okay? Because you are using the same JVM across multiple machines. Okay. Now there are some differences that you want to keep in mind in the RMI case. Yes, you have a question.
Sorry, I had a question on the previous slide. The question right there, what's the answer?
Okay, hold on, let me read what it says. Serialization of object parameters can be downloaded, constructed on the fly. Why can't this be done? I will have to get back to you on that. I'm not sure what it is referring to. Okay, so I made this slide some time ago, but I'll come back and describe what that was. Okay, so binding a client to an object. Okay, so here we are asking, how do you know that you are going to invoke a remote method on a remote object, and how do you locate that remote object? There are two ways to do this. One is called implicit binding, the other is called explicit binding. And there are two snippets of code that show you. This is not necessarily what Java does. This is just telling you how you are going to use RMIs in general across many languages. In some languages, we'll do implicit binding, which means the first time you make a method invocation on that object, the stuff will go try to locate that object. Okay? If you do explicit binding, you actually have to have a call which is saying bind, that is going to ask the runtime saying go find out where that object resides and figure out its IP address and so on and so forth. Okay? In implicit binding, that happens on the first call. In explicit binding, you have to make an explicit call before you can make RMI calls on that object. Okay? These are two different methods that both do binding. One is just happening at first invocation. The other is happening explicitly. So depending on the language, you will have to do one or the other. Okay? That will be the decision of the runtime system, whether it requires clients to do implicit or explicit binding. In either case, the server ought to have registered itself with the naming service. Okay, otherwise, the binding service will say, I don't know where this object is on the network. Okay, so that part is always explicit. The server has to explicitly register itself. How the client finds the server is either implicit or explicit. Okay? Okay, so there's one additional detail that I want to mention, which is actually different from the RPC world, which is we said in RPCs that all arguments to RPC calls are passed by value. We cannot pass pointers. We explicitly prohibited passing pointers because dereferencing a pointer on a different machine is meaningless because the pointer is a memory address on a particular machine. Okay, if you dereference it on another machine, you are going to look up that same address on that machine, which is not going to be meaningful. Okay? So Java has similar restrictions, but it does have more flexibility than that. Java allows you to do pass by reference in certain cases, not always. By default, it will still do pass by value, but in some cases, it will actually pass by reference. And this picture, which looks a bit confusing, but it's not really confusing once you understand it, shows you what the differences are. So here is the high level difference. If you make an RMI call, okay, and you pass a local object as a parameter, okay, you can also always pass integers and other things, but let's say you make an RMI call and pass a local object. Okay. That object will be passed by value, which means you will take that entire object, okay, its memory state, all of its code, and send it over to the other machine. Okay. And at the other machine, you have a copy of that object. And then if you need to access parts of it, in there you are going to make local call. Okay. So local objects, if they are passed as parameters, get passed by value. Okay. But you might actually have references to remote objects as well. If you pass a reference to a remote object, that will get passed by reference, and dereferencing it will actually result in a network reference. Okay? And that is what is shown in this picture. Okay? So it is showing two cases, passing a local object as a parameter, passing a remote object. And those two objects are O1 and O2. Okay? So you might actually say call, okay, so you might say, if you say foo.method, you can say pass O1. You can have another foo.method 2, you can pass O2. These are two arguments you passed. Both are objects. Okay? Just happens that O1 is a local object, O2 just happens to be a remote object. And see, here is what is going to happen. So if you now make a call, so here's your local object. You made an RMI call to machine C. Okay? And you passed O1 as an argument. So then what happens is the entire object O1 is passed as a parameter. Okay? And you will see now there's a copy of O1 here. Okay? Now if to execute the RMI call, you need to access any part of O1 or call methods on it, they actually go to O1. Okay? If in the meantime something has changed at the actual copy of O1, that won't be reflected there. That's something you got to keep in mind. Now if you make the second method call where you actually have a reference, a remote reference to another object. Okay? There's something called a remote reference, which is a reference to an object that resides on a different machine altogether. Okay? So the same machine A is now making a call, but it's passing O2, but it only has a reference to O2. It doesn't have the actual copy of O2 here. That is actually going to call a remote or be passed by reference, and it will come here, and when you dereference it, it will actually trigger additional calls to the actual object O2. Meaning there's only one global copy. If you make method invocations, it will go to that actual object. Here you will see that there are two copies. There's a primary copy and you made a second copy. So any method invocations here will change this state. When you made a RMI call, there are additional method invocations here, it will change that state. So that's the difference between the two. The higher level point is that you are able to pass certain things by reference, which we disallowed in the RPC case. Okay? The only things you are passing by reference are references to remote object. Okay? This requires you to, when you dereference, figure out where the object resides. Okay? Because typically when you are dereferencing an object, it's going to reside within that memory of that process. In this case, when you are dereferencing O2 here, you are actually going to figure out that it sits somewhere else and have to go to that object using additional RMI calls. Okay? Java is going to allow you this additional flexibility, which did not exist in RPCs. Okay? And in doing so, you also get some efficiencies, because you can imagine passing an object as a parameter. That's a lot of state you have to actually send over a network. You don't think of this when you're writing Java code where your process is local. But that's just a pointer inside Java. Java doesn't have pointers, but internally it's a pointer. But here you actually have to make a copy of that entire object. I mean, all of its code has to be sent over. Okay, all of the data that's in the object has to be sent over, which can get quite expensive. But if you're passing that as a parameter, that's what has to happen. Okay, is that clear? So there's that important distinction to keep in mind, which is that you can actually pass a pointer effectively. A remote object reference is a type of a network pointer. It's not a local pointer, it's a network pointer. Okay? We'll talk about other systems that you actually have the concept of a network pointer, which generalizes the notion of a memory pointer. Okay? Network pointer essentially says, I have a memory location and I have an IP address of the process where that memory location is valid. So dereferencing a network pointer essentially requires you to send a message to that machine and that location on that machine to figure out what the value is. Okay? That's a generalization of the notion of a memory pointer. Now most RPC systems don't have it, but there are some that will. Yes, your question. Okay, how do network pointers interact with Java's garbage collection? That's a good question. So garbage collection in Java essentially is going to go and delete memory that is not in use, specifically any dereferenced objects that are just sitting there and so on. Now if you have a network pointer, you could say, how, if the garbage collection runs on machine B, when does it know that it's okay to garbage collect O2? Maybe that's what you're specifically asking in this example, because you may not have any references to O2 locally here, but there are other machines that have use for O2. Okay, so the short answer is, if you have remote objects, you shouldn't garbage collect. The local objects you know, remote objects you don't know, because you don't know what other machines have. Yes, that's kind of the other. If you garbage collect, it will get an error otherwise. Okay, but that's a good question. Other questions here? Okay, anyone using RMIs for Java RMI specifically for the lab? Okay, so some of you, or many of you are. So you will actually understand some of these features if you use remote object references and so on. Okay, you can always use local objects. Lab 1 is pretty straightforward, but you can also use remote objects to make your RMI calls more efficient, not have to send lots of copies back and forth. Okay. Any other questions on this before we move on? Okay. So here are some other systems that have implemented other types of RMI systems that go beyond what we have looked at. Okay. These are specialized systems. You may not, I mean, at least this one you will not encounter anymore, because it's an old system that's no longer in use, but it had some interesting ideas. Okay. It basically had this notion of private objects and shared or public objects. Okay. What private objects are is basically a way to make RMI calls that essentially trigger request processing. So here are 3 clients. There's one server machine. Each of the client has made a request of the server using an RMI call. Okay. To service that RMI call, the server has instantiated a new object on the fly that is going to do the request processing. Okay, so think of a process request object that takes a request and processes it. Okay. So every time a request comes in or a RMI call comes in, you create or instantiate a new version of that object, and there is a thread created that only processes that request using that object. Okay. So there are 3 clients that have made 3 requests. You made 3 copies of that object. Each is processing that request using a thread. And once the request processing is done, the object is deleted. Okay. So this is a form of request processing where you instantiate an object. That object method will somehow process the request and the object will go away. Okay. It's an ephemeral object, doesn't exist beyond the lifetime of request processing. Okay. What you see in the second picture is what we have been talking about in the Java world. Once you create an object, okay, you allocate a new object, it will actually stay there. It's not going to go away once the request is processed. You can also make RMI calls on that object, and all RMI calls will go to the same object, okay, and they will actually change state on that object. Okay, which also means you've got to do synchronization on that object, because each of these requests, RMI calls, will be a thread that will invoke a method, or maybe it's the same method across multiple threads. And if they all change the state of the object, you need a synchronization. Okay. So if you are writing Java RMI code and you have multiple requests coming in that access the same state of that object, you better have some synchronization in your code. Otherwise, you might make modifications and have bad results because of race conditions. Okay. So this is basically the same as the Java world, where the object state is shared across multiple RMI calls that go to the same method, or same object rather. Is this clear, the difference between the two? Okay. Now this is something that was implemented in this runtime system called DCE, which was acronym for Distributed Computing Environment. It was a middleware that was built maybe 30 years ago now, 3 decades ago, that tried to implement a middleware system that had RPC and not RPC, RMIs and all kinds of other objects and so on. When we come back to middleware systems later on in this course, we'll come back to some of these concepts. Okay, but for now, all you need to know is there is this notion of a private object, which is a short lifetime object that's instantiated only for processing a request, or your shared object that have lifetime which is equal to the lifetime of the process. Okay, so let us continue. Let's say a few more things about Java RMI for those of you who are writing this code. So you basically have the server. Okay, the server has to define an interface. Okay, and then you have to have an implementation of the interface. Okay, the interface is what is exposed to the client, and the implementation is the code that is going to invoke when the client makes RMI call. So server program has to essentially create the server object and register the object with the remote object registry of some sort, which is this is the naming service. Okay. The client is going to look up the server in the remote object registry. Once it knows where the server is, you are going to use normal call syntax, which is object.method. Okay, it doesn't matter whether it's local or remote. So there are some tools like the RMI registry, which is the name server. There's a RMIC, I don't know if this is still what it is called, which is the RMI compiler that is going to generate the stub code for you. Just as in C++ and C or RPC Gen, you have similar tools in the Java world to create the Java stub code, the skeleton and the client side stub code for you. Okay. So I do want to mention synchronization, because if you write Java RMI code or any code that actually uses multiple threads or concurrence, you have to have synchronization in there. Okay. So like in any multi-threaded code, if you have an object that is receiving multiple RMI calls from one or multiple clients, you have to have synchronization. You should have synchronization in your server-side code. Okay. Fortunately, in Java, this is fairly trivial to do. Okay. You can take any object or any method of the object and simply add the word synchronized, okay, and you get automatic locking, which means that when you have multiple calls coming in, only one call will execute at a time. The runtime system will take care of that for you. You don't have to have explicit locks. When you add the word synchronized in front of any method of an object, that entire object or that method will actually get a lock. Okay. And in fact, all methods that have the keyword synchronize in front of them, all of them will get one global lock for that object. So you can only execute one of those methods at a time, which gives you automatic synchronization. Okay. So multiple buy requests come in your lab, for example, and you have only one item to sell. The first one will succeed, and the next ones, if they actually execute, will see that the object is or the item is sold, for example. Okay. So you can do this very straightforward manner in Java by using this notion of synchronized. Okay. Having said that, there are some additional complications that we have to deal with, which are essentially how Java runtime should actually implement the synchronize. Synchronize was not designed for RMIs, it was designed for just Java threads. Okay. You can just write a normal Java program with multiple threads in it, and just synchronize is a keyword that allows you to add synchronization to your code. Okay. Same concept is going to apply to RMIs, except that you got to deal with where blocking has to happen. Okay. If two clients make the same RMI call, okay, one of them will succeed, the other one will have to wait. Okay, that's what blocking or synchronization would mean. Question is, where should you block? Okay, you have two options, which is block at the client, or proxy is the same as the client, or block at the server. If you're blocking at the server, both calls come into the server stub. The server stub implements the synchronization. And one of them succeeds, the other one waits. When the first one finishes, the next one executes. Okay. If you implement synchronization at the client, you are basically, all the clients have to coordinate, only one of them gets to actually make the call at a stub code level. None of this is dealt by the programmer. All of this is happening in the stub or the runtime system. Okay. The second method actually needs the notion of a distributed lock, because the clients collectively implement a single distributed lock for each object, and they have to explicitly grab that lock inside the stub code before they are allowed to make the RMI call at all. Okay. Again, you don't deal with it as a programmer, but the stub code has to deal with it. And when we come to the next chapter, we will actually look at how to implement a distributed lock. But that is what has to happen, because all the clients are coordinating. If multiple of them have to make the same RMI call, they will first try to grab your lock. Okay. And then whoever has the lock actually gets to execute, meaning gets to make the RMI call. In the former case, the server is implementing a lock in the server process. The stub code will simply try to grab the lock, or the thread in the stub code will grab the lock, and one of them will succeed. That's just a standard lock. Okay. Is that all clear? Any questions on this? Okay, we'll come back to how to implement distributed locks later. Okay, we haven't actually studied how to do this, but that's an interesting problem in its own right, which is how do you take the notion of a lock and make it distributed, so multiple processes can coordinate and try to grab the lock, just as you can do this within threads of the same process. Okay, so with that, I'm going to switch gears. I'll see if there's any questions, and if not, we'll switch gears and talk about socket programming, which is programming at the lowest level of the network protocol stack, right? Meaning you are basically going to do low-level network programming as opposed to using things like RPCs and RMIs and things of that sort. Any last questions about RMIs? Is anyone using raw sockets to write their lab? Okay, nobody is. All right. You have that option, but since you are not using it, this is the picture you want to keep in mind, how to use raw sockets at all. So the way you do socket level programming is the programmer has to actually write code to establish a connection between the client and the server, construct a message, send that message over, understand what that message is, process it, and so on. So all of that code has to actually be written by the program. You get a lot of control over what is actually happening in your code, but you also have to write a lot more code than you might have written if you used RPCs or RMIs. Okay? And this is basically, this picture is showing you a standard client and server communicating with one another using socket code. Okay? This is basically a very standard way to write socket code, where the server is, these are all system calls, by the way. So server makes a socket call to establish a new socket, then it binds the socket, then it starts listening. okay, which says now it's ready to start accepting requests from the client. Okay. And then it's going to sit in a loop with an accept call. Accept allows it to accept a new request from a server. Okay. And then I'll come back to read and write. And then the client, in order to communicate with the server, also has to create a new socket by making the socket call. Okay, and then it has to call the connect call to connect with the server, where you will specify the IP address and the port number. As it says, so connect is going to say set up a TCP, or it could be if it's a UDP, you will not do it this way. Set up a TCP connection to the server at this IP address and this port number. And then when that connection is made, the accept call will return and a new TCP connection has been established between the client and the server. Okay. At that point, it's a duplex connection. So the client and the server can communicate using read and write calls or send and receive. They're both equivalent. Okay. Send will allow you to send a message, or you can write to a socket, which is the same as sending a message. If you read from a socket descriptor, you are reading or receiving messages. Okay. So you are going to use send or receive or read or write for messages to go back and forth. Once all of the communication between the client and the server is done, you are going to close that socket, which will tear down your TCP connection. Okay. So all this has to be written by the programmers in their code in order to use socket communication. And then what the server is going to do is it's going to sit in a while loop where you will essentially have an accept. And then once the connection is received, you might actually hand it off to a thread or something to a process, or do those read or write, or you can just do sequential processing as well. Okay. So this is what is called Berkeley sockets, because that's basically standard way to write Linux code or Unix code or any POSIX code for that matter, even in other platforms such as Windows or Mac OS X. Okay, so there are these primitives I talked about, which I'll briefly mention. Socket creates a new connection. Okay. Bind attaches a local address to a socket. It binds a port number. Listen says that I'm willing to now accept new connections on this socket. Okay. Accept essentially waits for a new connection to be made from the client. Okay. And then connect is the client side code to actually connect to the server. Okay. Send receive, which is the equivalent of read write, are essentially going to send data over a connection. Close closes the connection. Okay. So all of this in the RPC case was done by the stub code for you. You did not have to do this. Neither did you even have to construct the structure of the messages and so on. Because when you do read or write, you're actually sending messages. You have to decide the structure of the message, saying the first field will contain this and the second field will contain this and so on, and send that over. Okay, all this is simplified for you when you program at RPC or RMI level. Okay, so that is Berkeley sockets. And then I'm going to quickly talk about MPIs, or message passing interface, which generalizes this notion. We'll continue that discussion maybe next time. Okay. So in the case of MPIs, what you have is a specialized library that is designed for parallel processing. Okay. Very high throughput parallel processing on a cluster of machine. And the reason they came up with this library is, in many cases, the overhead of TCP was much higher than you wanted. And second is, some of the abstractions given by normal sockets was also not what you might have wanted. Sockets do synchronous communication. If you want to do asynchronous network I/O, sockets is not what you want to use, because sockets will be blocking calls. Okay, except all of those are blocking calls. So MPI essentially is a generalization of what the socket interface does. It allows you to do asynchronous sending and receiving. Okay. It allows you to use protocols that are not necessarily TCP based. Okay, you might have send and receive calls, but they may not use TCP underneath. They can use other protocols that may be specific to parallel programming environment. Okay. So it decouples the sending and receiving of messages from TCP. It also decouples the communication using socket style low level interfaces from being synchronous. You can essentially use asynchronous calls as well. So there are a whole set of calls, and I'll show some of these in just a moment. So this is called message passing interface, or MPI. This is broadly used for parallel programming. You will not see this in normal client server environments. But if you have a parallel machine, Okay, and you are writing highly parallel code that runs on different nodes of the machine that want to have high throughput communication, you will actually use MPI libraries, or you might use MPI libraries to achieve this, because they give you higher low efficiency way, or not lower but better efficiency when you send messages back and forth. Okay. Here's a set of calls that should give you some notion of what I was talking about. Okay. So you will see that now there are several variants of send. Okay. In socket there was only one send, which was your write call, which was blocking. Okay. In MPI there are 6 or 7 different variants of send, and you will see that they actually map to different types of asynchronous or synchronous communication between the two machines that are communicating. Okay. So bsend essentially says append the message to the local buffer. Okay. So it's an asynchronous call. It says just copy the message I want to send to the OS and return, okay, and then send it out asynchronously. You're not waiting for an acknowledgement from the OS, not waiting for an acknowledgement from the other machine, and so on. Okay. Send is essentially going to wait until the message is typically copied to the remote buffer, which means you wait for the message to have reached the other end, you get an acknowledgement, and then you continue. You're not waiting for the reply. Send is going to send a message and it waits for the other process to take delivery. Okay. The difference between these two is in send you wait for the message to receive have been received by the OS at the other end. In the second case, you wait for it to be received by the application at the other end, which are two distinct things. Okay. Send receive essentially sends a message and waits for a reply. That's the equivalent of RPC. Send a message and you block for a reply to be received. Okay. iSend essentially doesn't even use buffers. It is using memory pointers to essentially pass messages. So you are actually reducing the overhead of memory copy to the OS as well. Okay. And then there is a ISS send, which says send a message and wait for the reply to be. So you will see that what MPI has done is it's taken this notion of a send and made it asynchronous in many different ways. Okay. Do you want to know that the other end, OS has received the message? Do you want to know that the application at the other end has received the message? Or do you want to just give it to the local OS and continue? Or you want to block until the reply is received? So you can do all of those things. Okay. Now, as a programmer, you have to decide what makes sense for your application. MPI is giving you a flexible library, okay, but it's not going to tell you which ones to use. Okay. You have to decide as a programmer saying this is what makes sense. Okay. In socket programming, there was no such flexibility. Everything was synchronous. There was only one send and one receive. Okay. And here you do have two types of receive. One is a blocking receive, which is going to wait for a message and otherwise block until the message is received. The other is a non-blocking receive, okay, which basically says check if the message is arrived from the client. If not, return, saying there's no message. So it's like polling. You're polling for a message. If the message is received, you return with the message. If not, you're going to return saying there is no message that has been received. Okay. So this is how you are actually going to write parallel programs, because you want higher efficiency. So you can get the right level of efficiency by using the right type of asynchronous program. Okay. We haven't talked about much asynchronous programming until now. This is our first encounter of asynchronous network programming. There's also asynchronous I/O to disk, which we have not looked at all. But MPI essentially does this at the network level. Okay, any questions here? Okay, so we have a few minutes. So I'm going to actually take a pause here and see if people have any questions about the lab that I can answer to the group and also to the online class. There have been lots of questions coming up on Piazza. I thought I can spend maybe 5-10 minutes to see if there are any high-level questions you want to ask. Okay? But before I open it up for question, I do want to say one thing, which is if you actually hopefully all read the lab specification by now. If not, you should, because time is running out. The lab is specified in a way that leaves a lot of design decisions in your hands. Okay? It's not meant to be we give you a detailed spec, you just go write code for it, because that is not what a graduate level systems course is supposed to teach you. Okay? The goal is to teach you to be system designers or system architects, not to be programmers. Okay, programmers get a spec, they just write code based on the spec. System architect get a high level problem description and construct a design that actually is efficient to solve that problem. Okay? So you will see that a lot of design decisions are left to you. What peer-to-peer network topology to use. You get to decide. You even get to decide what language to use. Okay? So that's a deliberate decision so that you understand the implications of the decisions you make. Okay, you might make mistakes and that's okay, right? Because that what you decide now may not work if you want to scale it up in a subsequent lab and so on and so forth. But that is how you are going to learn what's the right level of design decisions to make and so on. Okay, so you might have lots of questions about what should I do in this case and what should I do in the other case. Feel free to ask us questions, but many times the answer is going to be it's up to you. Okay? And that is the way you are going to learn how to design systems. That's the way you learn to do systems research as well. But at the end of the day, this is a core course that's designed to actually teach you something about systems. Okay? Having said that, let me see if you have high-level questions you want to ask about the lab. Yes, please.
So will future labs then extend what we've done in this current lab?
Okay, question is just future lab extend what you have done in this lab. What is going to happen is you are going to program at different layers. So it's not going to be fully dependent. Here you programmed at RPC layer. Next lab you are going to use REST interfaces, which are HTTP. You may not reuse any code at all. You might implement similar functionality, but using a completely different set of abstractions. In the last lab, you might do microservices, which is break up your code into smaller pieces. So there is no wrong thing you can do now that you have to think about the future. But having said that, you should think about what are the right design decisions that will allow you to make sure that you can use these same ideas, but you have to re-implement them. You're not going to be able to, most likely, you're not going to be able to take the code and use the same code. Okay? But the ideas can be reused if you come up with good designs. Okay, yes, question.
The instructions kind of insinuate that there's not supposed to be a join or leave function, and that when we test our code, you should just start the system and
Yes.
have it work. So should we contain the entire lab in like one method call that's just like start the system, so then it moves
Yes.
to the same place?
Okay, that's a good question. The question is about how to construct the P2P topology. Right? Typically, if you implement a P2P system, you have to deal with dynamics, where peers come, peers go, and so on. To keep the lab manageable, at least the first lab manageable, we did not ask you to deal with dynamics. So you don't actually have to do leaves, okay? But you do have to do joins because you have to construct the network. Okay? The joins could be all peers join when the system starts up. Okay? Or you can basically have them join sequentially, saying the first peer joins, then the second peer joins, the first peer, the third peer joins. And then once the entire network is done, then the requests actually start flowing through the network. Okay? So think about joins, but you don't have to worry about leaves. It simplifies quite a bit of your design. Okay? Yes.
One of the questions indicated that you have to put the peers in different folders, but if I'm selecting the buyer and the seller on the fly, what should I do?
Okay. The question is, it's a part of the lab. It says put the clients in different folders, and how do you deal with buy and sell requests and so on. Okay, so the lab had multiple parts. The first part of the lab says show that your code works by initially just running the peers on the same machine. Okay? And it said if you could make copies of your code in multiple directories and just execute them, but how you choose to execute peers on the same machine is up to you. You don't have to use folders. You can just start 5 copies of a binary. We don't have any problem with that. Okay? The second part of the lab said, now show that your code actually works as a distributed system, which means it has to run on at least 2 machines. Okay? It could run on more. If you can show more, that's fine, but 2 is a good number. You can't say my code runs on 1 machine, hence it's distributed. The whole point is it has to run over a network. Okay? And as you will see, you're probably finding that when you're running things on NATed machines with a private IP addresses, things don't work as you think. This is where you learn something about systems as well. Right? So some machines are public IP addresses, some are private IP addresses. Making it work across all these things is harder. You can certainly run all of your code on EdLab machines, all public IP addresses, and say it works. But you have to at least run it on 2 machines. Okay? If you choose to run on your home network and other machines, you need to know how to make NAT, firewalls, all of those things work. Okay, that's again up to you. You can simplify your life and just run it on EdLab. That should be fine. There are no firewalls there or any public IP address machine. Yes.
So if Pierce runs on two machines, then how do you use the join problem?
How do you use what?
The join problem, like some peers join the network.
Okay. Question is, if peers run on two machines, how do you do joins? Okay, the joins are going to construct your network topology. It's independent of what machines the peers are. Okay, all that the join says is this peer can communicate with these two other peers directly. So think of a ring as a topology. If you pick the ring, you have to basically pick a right neighbor and a left neighbor. Okay? It doesn't matter where those peers are. They could all be on the same machine, but you still, of all the n peers, you got to pick one peer as your left neighbor, one peer as your right neighbor. And those are the ones you communicate with. Okay? So same is true whether you are on the same machine or not. So the join essentially construct the P2P topology, whether you use unstructured or whether you use ring topology or some other topology. That's again your design decision. But the join will say this peer has direct communication with these two other peers. Everything else is multiple hops away. Those are the only peers you can talk to directly in your P2P system. Okay. Yeah, any other questions here? Yes, please.
Are we expected to implement the P2P topology from scratch?
I did not. Your question is, are you implementing the P2P topology from scratch? Can you elaborate what you're asking? I'm not sure what you exactly meant.
Like, so do we have to like construct a hash table by ourselves to hold the nets or something like that?
Okay, so if you're asking, do you have to make a DHT? Is that what you're asking? So you have to construct a peer topology. You don't necessarily have to do it using a DHT. You can make a random topology, which is unstructured, which every peer makes k connections. Let's say k is 3. So of all the peers, you are going to pick 3 random peers and make connections to them. Every peer does the same thing and you get a topology of some sort. Okay? You could also use CORD, which is a ring topology. Okay, so the topology is up to you, but you don't need to implement a full-fledged DHT for this lab. Okay? Yes, please.
I'm curious whether, in general, people have requested to use other programming languages or if they've been sticking with.
Okay, question is, have people used other programming languages or not? We have received requests to implement things in Scala, in Erlang, in Rust, Go, and then of course Python, Java, C++. So I think there will be a broad spectrum of programming languages. Assuming people actually went ahead with we said fine. As usual, it's up to you. But we did ask whether the only requirement is that you use native or low-level RPCs. Don't start doing things using REST interfaces, HTTP, XML RPCs. That's coming in lab 2. Okay, so long as you use threads, native RPCs or RMIs of some sort, it's fine with us. Okay? Any other questions? Okay, so let's end it here. Feel free to post on Piazza. There are office hours by the every day of the week. Okay, I'm going to post them again on Piazza if you are not clear what they are. But there's somebody available to talk every day this week. Yes, I will be.